Okay. Good day, good day, good day, and welcome to Africa Teen Gig. And we present to you the STEM Digital School. This is our online school, as you know it. If you've just joined in this classroom, this is the grade 11 physical sciences. The grade 11 physical science. Today is the 3rd of July 2020, and it's a Friday. I hope that everybody is having a great time, a great day, and ready to do some physical sciences. Yes, indeed, I just want to remind you that most of the work that I'm doing here on this in this classroom, it's from the Oxford Successful textbook, but I also use the Siavula textbook and the Study and Master. So in any textbook that you are using, it's still good as long as it's CAPS approved. You'll be able to relate to anything that I'm teaching right here. And besides that, you can get free textbooks on Snaplified. You can download Snaplified. It's an application where you can just search any textbook and you'll be able to find it there. And not just for physical sciences, but all your other subjects as well. So if you are in need of textbooks or you feel like there's others that you can refer from, you can go to Snaplify and download yourself some good textbooks. My name is Nonkululego Madondo. I am your physical sciences grade 11 teacher, and I hope that you are having a good day today. So another thing that I wanted to let you know is that as I'm teaching this class, you guys are allowed to ask questions through the chat. Anything that you feel you're getting stuck or you want some more clarity, just send a chat and I'll try my best to explain whatever or wherever you are getting stuck. Because the aim here is for us to understand and to master this physical sciences that we are doing this year. Oh, and I forgot to let you guys know that on the Snaplified, the textbooks are free for the rest of the year. You can even view them offline. You don't have to have internet to view those textbooks. As long as you have the app, you can open them at any time. It's all these textbooks are going to be free until the 31st of December because of the COVID-19 problems that we had. So if you do get a chance, please, please, please get yourself some textbooks and get yourself knowledgeable. I also wanted to tell you guys, today we're going to be doing electric field strength and magnetic field. Why are we doing two things in one day? That's because some of them have calculations. Remember, with the revised, with the CAPS revised ATP that I've been showing you for the past few days, it states that in this for electricity, the part of electricity and magnetism, there will not be any calculations in the end of the year exam. So I'm only touching the parts where the theory parts, because they will still ask you theory, they will still ask you the formulas, but they will not ask you to do the calculations. So bear in mind with that, and hence I did skip the column applying the columns law. But we did do the columns law, so it's not such a big train smash, but it's got too many calculations. And remember, we're not doing calculations, so I don't want to stress you guys with work that is not going to make you pass. Okay, kudos. So now, let me see, what have we been doing here? Okay, this is homework that we already did. Okay, I think I might have taken the wrong homework for us, but nonetheless, let's continue. I'll just check it, and if we still have time, I'll be able to go back and review it for you guys. Okay, so let's get started. What are we going to be doing today? Today we're going to be doing electric field strength. We're going to do the forces of electric field, the electric field at a point, and electric field with more than one charges. Okay, and then for the magnetic field one, it's a very very short chapter. So they actually merge well together because they both short if you minus the calculations on some of the parts, which is in the electric field strength. Okay, so there we're going to be doing magnetic field of an electric current, and we're also going to do the right hand rule. I will try my best to go back to our textbooks and see if we can't have like more examples that you guys can possibly try to do on your own and see if it can work out. Okay. Oh, here's the homework that I'm looking for. Okay, we did most of these problems yesterday, if you guys remember, and I last said that you guys can do number 5 for me. I hope that most of you guys have done it and have all your answers right. So the first one is, I said you guys must do number 5, right? Because we already did all these ones yesterday together. So on number 5.1, it says, what is meant by the description uniform field? Okay. What is meant by a description of uniform field? So it says here that a uniform electric field is the same everywhere, and the force on a particular charge is the same no matter where it is in the field. Are you guys with me? Do you guys understand? So that is what is meant by uniform field, is that a uniform electric field is the same everywhere, and the force on a particular charge is the same as well, no matter where it is on the field. Okay, guys, remember these terms are very important. You need to know them because they're going to help you, especially um, on your multiple choice questions. You know, those short questions where the true or false, these are the type of things that they ask. So you must know this. But uniform field, I'm sure it's not difficult to memorize because you just know that it's the same. Uniform means something that is the same. So you can just say it's the same everywhere, and the electric field is the same everywhere, and the force on a particular charge is the same also, no matter where it is on the field. Okay, so number 5.2, it says, describe how to set up a uniform electric field. Okay, how do you set up a uniform electric field? So it says here, give an opposite charge to two parallel plates. So it would be an arrangement similar to this one. Okay, so give an opposite charge to two parallel plates to obtain a uniform field. Okay, so you connect one of the two parallel metal plates to the negative and the other to the positive terminal of the direct current energy source. Okay, I hope you're writing them down or you're marking what you've done correctly, and you understand where you made your mistakes, or your stuff is just perfect and you can continue. Okay, so on number 3, it says, explain whether the acceleration of a charged object in a uniform field will also be uniform. Okay, explain whether the acceleration of a charged object in a uniform field will also be uniform. Okay, so what it says here, it says the force on a charged object is uniform, which is true, and so its acceleration is also uniform. Okay, because they are directly proportional to each other. Okay, so the acceleration is proportional to the force. Okay, I hope you got all your answers right. Okay, so now we're getting started with the electric field strength. Ooh, this one is so huge. Forces of an electric field. Okay, so what we need to know when we talk about electric field, that the stronger an electric field, the stronger the force that is exerted on the charge. Okay, so if an electric field is strong, it means that the force that's exerted on the charge will also be strong. Okay, so force on a point charge can be determined through the electric field, the electric strength, or the intensity. The force on a point charge. So if you have your charge there, you can the force can be determined through the electric strength or intensity. Okay, so if you know the electric strength or intensity, you can find the force on a point charge. Okay, so the electric field strength at a point in an electric field is the force per unit charge experienced by a charge placed at a point. So that is the meaning of an electric field strength. So basically, in plain English, it says when you have your electric field, the strength of it, that is what your electric field strength is. It's basically the intensity or the strength. Okay, so the electric field strength at a point in an electric field is the force per unit charge experienced by a charge placed at a point. Okay, guys, if you do get a bit stuck, just let me know. Send me a chat and I'll explain where you're getting stuck. Okay, so a small test charge, which could be Q, a small letter Q. Remember we spoke about what's a test charge. A small test charge Q is placed near a charge. So if you've got the big Q there, which is a charge, and you bring in a small test charge, which is a small letter Q, will experience a force due to the electric field surrounding Q. Okay, so this one, the small one, will experience a force due to the electric current surrounding Q. Remember, yesterday we spoke about that if a big charge is placed next to a small one, it will be the one that determines the direction of the field lines. Remember, we spoke about that yesterday. So that's basically what it explains here as well. Okay. So the magnitude of the force is described by Coulomb's law and depends on the magnitude of the large Q. I'm sorry about that. Magnitude of the large Q and the distance of the test charge from Q. Okay. So at the end of the day, Coulomb's law plays a big part in the electric field. As you've seen, we always keep referring to the Coulomb's law. So it also depends on the magnitude of the large Q and the distance. Because remember, on the Coulomb's law, everything is indirectly proportional to the square distance between the two charges. So because that part plays a big role here, it has to also influence the magnitude of the force as described by the Coulomb's law. Okay, because the force is indirectly proportional to the square distance of the two charges. So the closer the test charge Q is to Q, to the large Q, the greater the force it will experience. So what this basically means, it means that the closer two charges are away from each other, the greater the force will be between them. Because you remember, guys, what I mentioned to you guys yesterday is that the further the electric field the electric field moves from the charge, the weaker it becomes. So that's what it means here. So when you put the two charges together, close together, it means that it will be strong because they are much closer together. So it doesn't take them a long time to get to the next one. So the electric field becomes more and greater. Okay, so a point closer to the charge Q, the stronger its electric field. Okay, so this is a new term that we need to know, which is force per unit charge. Force per unit charge is the electric field at a point. Okay, so these are similar terms of each other. Okay, so the force per unit charge is the electric field at a point. So remember, our electric field is denoted, let me see, I think we do have, I'm just trying to go to our previous page so that I can show you guys. Okay, no, we do not have it here. But basically, you remember those lines that we spoke about? Those lines that we spoke about around, like when you have a Q here. Let me just see if we can get one from the Snaplify textbook. Hmm, okay, it seems that we do not have our textbook in place right now. But basically, what this means is that when you have your Q here and you have all these electric fields, remember they are denoted by this the lines, the electric field lines. That is a strength, and they get shorter as they move further apart. Just remember that part, guys. That the further they move, the weaker the electric strength becomes. Okay. So moving on to the next one. Okay, now we get back, we're going back to the electric field. We've already spoken a lot about the electric field, but here we need it because it's part of the definition that we need to to acquiring our electric field strength. Okay, so that's why I brought it back here. So what is the definition of electric field? Electric field is the magnitude of the electric field E at a point can be quantified as the force per unit charge. Okay, so this is a force. The electric field is a force. Okay, so that's why it's got the power to repel with other charges, or attract them because of the electric field, because of the force that exists between the charges. Okay, they either accept each other, or one is repellent and they push each other away. So that's why an electric field is a force, because it is between the two charges. Okay, so written as an equation, we're going to have E is equals to F over Q. F is the force. Both E and F are their quantities. So electric field strength is measured in newtons per coulomb. Okay, the N per C. Okay, so A unit charge is a charge of 1 coulomb. Q is a charge placed at a point in the field. Okay, so remember the Q. It's a charge placed at a point in the field. It is not the source of the field. So it doesn't create the charges as you see them placed, as much as they showing the electric field strength or the electric field lines. They are not the source of the field. Okay, they just happen to be placed at a point in the field. Does that make sense, guys? I hope that it does. So both E and F are vector quantities. Electric field strength is measured in newtons per coulomb. Okay, let's move on. So the equation for electric field at a point. Oh, here we have something. So this is your charge. This is your big charge, and this is a small charge. Remember we spoke about the big charge and field charge. So what they mentioned now before is that these ones, the Qs, these two Qs, they are not the source of the electric field. Okay, they are placed at a point in an electric field. So the electric field was there, and then they placed two charges there, okay, at a distance from each other. So when 2 point charges, for example, in this case, it will be Q and Q at a distance R apart on an electric field, Coulomb's law states that the force Q and Q is the force is directly proportional to the charges, and indirectly proportional to the distance squared between the charges. So that's how we find our force. Okay, so the force Q on Q is this. And then we move on. Now we want to know the electric field strength is therefore, because remember, this is our topic. Today we are dealing with the electric field strength. So the E, which is this one, okay, pay much attention. The E is the equation, right? The electric field strength is equals to F over Q. Okay, it's equals to F over Q. But what is Q in this case? What is F? Then you're going to take this equation, which is your electric field strength equation, and you're going to substitute what you have for F here. Okay, so E is equals to F over Q. Then you substitute what you have for F, and that will give you KQQ over R squared divided by Q, because remember, this is the Q that we have from the equation. So what will happen is that these two Q's are going to cancel each other out, and this will be the equation for your electric field strength. So you see there's a difference. So they can even ask you in a question that is this an equation for electric field strength, or is it an equation, or is it the columns law, So you need to know the difference between the two. There's a very big difference between the two, because remember that other equation, it's got Q and the small q over R cubed, but this one, it's just the big Q over R squared. Okay, so this is important. You need to know the difference between your electric field and your Coulomb's law equations. So the electric field strength of a point charge Q is proportional to the size of the charge and inversely proportional to the squared distance from the charge. So, which means the electric field strength only worries much about this big Q. And why is that, guys? Why is the most important part? Why does the electric field strength focus on the big Q, on the big charge? I'll tell you why. The reason is because this one, because it's much bigger than the small charge, it is the one that will 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 determine the direction of the electric field. So it's basically the one that's in charge. So that's why when you check the electric field strength, we calculate according to it, because this one doesn't have a say on the direction of the electric field because of the big Q, the big charge. Okay, so the direction of electric field strength vector is the same as the direction of the electric field. Okay, are we together? Any questions moving forward? We good? Okay, so now we're going to move on. That was just the short theory on electric field strength. I hope that you are content with everything, because we've managed to cut out all the all the calculations. That's all the theory basically that you need to know when it comes to the electric field. Okay, so now we move on. We move to the magnetic field of an electric current. Okay, so we've spoken about the electric field. Now we're talking about a magnetic field, but of a electric current. So what do we need to know about the magnetic field? A magnet has a pair of two opposite poles. So a magnet, which is what we have here, has a north pole and a south pole, or N pole and S pole. So it's got two opposite pole pairs. Okay, so whenever you put two, whenever you have two magnets, and whenever you have two north pole magnets facing each other, the like poles will repel each other. So this is also similar to the electric charges, whereby if if two are facing the same, two are both positive, they will repel. But if they are one is negative and the other is positive, they will attract each other. So it's the same case with magnetic field, okay? Um, two magnets, like poles, will repel each other, but unlike poles, will attract each other. Okay, so a magnetic field can be produced by a flow of current or a magnetized material. So you need a magnetic thing or a magnetic object for a magnetic field to be produced. Okay, okay. My apologies for the bad network. Um, where was we? Oh, here it is. Okay, so we're still talking about the magnetic field. I'm just not sure. Ah, okay, I'm just not sure where the network cut off or when I just saw it reloading. So I'm just going to start back from the magnetic field of an electric current. A magnet has a pair of two opposite poles, the north and the south pole. So when you put two poles that are alike together, um, two north poles, magnets facing each other, they will repel, and unlike poles, will attract each other. This is similar to the electric field, but in this case, it's with the magnets. It's not the charges. It's the magnets. So if they are similar, if they are both north, they will repel each other. They will not attract each other. So a magnetic field can be produced by a flow of current or a magnetized material. So you need a magnet or a magnetic material for a magnetic um, field to be created. Okay. So another thing that you need to know is that in a pole of a magnet will will the magnetic field will be felt by any particle that gets attracted or has a magnetic property around it. Okay, so here we've got a small little example. They have a compass needles and iron fillings reveal that magnetic field of a bar magnet. Okay, so it shows that the a magnetic field surrounds a current carrying wire. Okay, so this is an example of how it would look like if you had to test the magnetic field strength, okay? So this one is visible. It's not like the electric field where you couldn't see what you were doing. You just had to make imaginary lines to demonstrate where it could be. With the magnet, it's actually a visible test where you can actually see the pattern of the magnetic field and how far it goes, okay? Okay. So I'm just trying to move on to the next page. So moving on to the next page, luckily for this part, there's not any equations. Everything is just theoretical. So we're moving on to the right hand rule. I'm sure you've heard of the right hand rule, but we're doing the right hand rule again, okay? And you're going to have it even in university when you go do science subjects. You will come across the right hand rule. So the right hand rule describes the relationship between the direction of a current and its magnetic field. Okay, so the current direction is upwards and the magnetic field is anti-clockwise. Okay, so when viewed from above, so if the current is reversed, the field is in the opposite direction. So this is quite simple to see. Okay, so you put um, you hold with your right hand, you hold between the direction of the current and the magnetic field. Okay, so as you can see here, so this is if the thumb is in the direction of the current, so this thumb here is showing the direction of the current. Okay, so the current is flowing downwards. Okay, so the curled fingers will be the direction of the magnetic field, so which means the direction of the magnetic field is going clockwise. Okay, so if it's reversed, alternatively, it will be anti-clockwise. So the right hand rule basically is just to show you how the direction of the magnetic field. So that's what it's all about. So it shows you the thumb. You always put the thumb, you're using your right hand, no, not the left hand. When you're using your right hand, um, and you're pointing in the direction of the current, the 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 direction of your coiled hands on the right hand, they will indicate the direction of the magnetic field. Okay, so this, guys, very much important. You will definitely be asked about the right hand rule, so make sure that you understand it, but it's quite simple to understand. Okay, and then now we're going to the right hand rule for a solenoid. Okay, so this is our solenoid. You can see there, this piece of copper wire. Okay, I'm sure you know them, um, as much as they're not shown in detail. But what it says here, it says if the curled fingers are in the direction of the current thumb of the current. Okay, so in this case, now we don't the the thumb is not the one that indicates the current in the solenoid part. It's the hands. It's the hands that show the direction of the coil. Okay, so if the curled fingers are in the direction of the current, the thumb will be the direction of the magnetic field inside the solenoid. Are we together? I hope that it makes sense to you guys. So basically, they're different. They both the right hand rule, but they work differently. With the normal one, the is what, but with the solenoid, you use your curled fingers as the direction of the current, and your thumb becomes the direction of the magnetic field. But on the other one, um, the thumb is what shows the direction of the current, and your curled hands are the ones that show the direction of the magnetic field. Okay, are we together? Any clarity? Are we good to go? Just let me know on the chat. So I think that would be the end of our presentation. But as usual, there's always something that we can do. Okay. So it says here, state the right hand rule for a current and its magnetic field. State the right hand rule for a current and its magnetic field. So can you please just state that down for me, and just send it to me in a chat. I want to know if you have mastered the right hand rule for a current and its magnetic field. Can you please write it down for me while I continue with the other questions? So that's number one as a class activity. Okay. So number two says, refer to the demonstration of the field around a current carrying conductor. It says on number 2.1, describe the purpose of the magnetic compasses. And then number two, describe the shape of the magnetic field around a straight current carrying conductor. Okay? Oh no. Yes. So please, if I get an answer for number one, I'll be able to show the answer for number two. Okay? So on number 2.3, it says, explain the effect on the compass needle if number 2.3.1, the current in the conductor is reversed. Number 2.3.2, the switch in the circuit is opened. Come on, guys. Um, the current carrying conductor, the right hand rule is not so difficult. Just write it down for me so that we can continue. Okay. But here we are with the right hand rule. So here is what it says on the right hand rule. It says if the thumb is in the direction of the current, the curled fingers will be the direction of the magnetic field around the conductor or through the loop. Okay, not so hard, is it? It's quite easy. You just have to memorize it and know it. Okay, so moving to 2.2.2.1, it says describe the purpose of a magnetic compass. Okay, the answer here is if a compass needle deflects or changes direction, it indicates that there's a magnetic field in addition to the Earth's field. Okay, so they're asking describe the purpose of the magnetic compass. Okay, if a compass needle deflects, it indicates that there's a magnetic field in addition to the Earth field. So this is all scientific. This is what the scientists use, to see if there's magnetic field around the area. Okay, so if the compass needle deflects, it indicates there is a magnetic field in addition to the S field. So they usually do it when they go there on site and try to find places where there's magnetic field. Okay, so number 2.2 says describe the shape of the magnetic field around. Describe the shape of the magnetic field around a straight current carrying conductor. Okay, describe the shape of a magnetic field around a straight current carrying conductor. So, the magnetic field surrounds the wire conductor and it's circular. Okay, remember it looks almost something like this. You see, this one it's very circular. So this is what they mean when they talk about um, it's circular, because you see this one is a straight as well conductor. So it just becomes circular. Okay, so 2.3 it says explain the effect on the compass needle If number 2.3.1, the current in the conductor is reversed, number 2.3.2, switch, the switch in the circuit is opened. Okay, so I'm going to give you the last one as homework. Please go and do it. um please go do this one for me, and tomorrow we can first start with this problem, and do this one before we do the next work for tomorrow. So that is it from me. And thank you so much for joining me for Physical Sciences Grade 11. My name is Nonkululeko Madondo, and I am the teacher. You can get me. Oh, I forgot to change this part again. My email is T for Thomas 33 T for Thomas again, NDLOVU. So it's T33T Ndlovu at gmail.com. If you have any further queries with regards to physical sciences or what we are doing at the current moment, please let me know, holla at me, and I can try my best to help you. Thank you guys so much, and goodbye.